Hello. In my previous video, I used the block decomposition method to compute the complexity of an application based on its network of services. This time, I'll examine a way to compute the importance of each service in an ecosystem. Just like when I showed that you couldn't judge complexity based on simple measures, I'll show that intuition is not always intuitive when determining importance either. Here I drew a graph of the network of services that a real mobile app uses. Since this is a small app, it only uses three types of services: web requests, web services, and database services. When doing graph computations, we take into consideration all of an app's services, because if we exclude any, like all web requests, we get an unconnected graph object. To Dynatrace, an application is the front-end part that a user can access via a web browser or a mobile device. So Dynatrace will not show an app connected to another app, nor will it show an app dependent on other apps like this. Therefore, to determine dependence, we need to look at the importance of the shared services that are used by many apps. Here's a visualization of the service network used by a real web app. Even though it's only a medium-sized app, I needed to have Python generate this graphic because the connections between services grows very quickly as app complexity increases. For my analysis, I looked at apps in an ecosystem that are monitored by Dynatrace and have been used within the past 3 days. Packaged commercial apps look monolithic in Dynatrace, so I only examined the 120 custom apps that call services. As a side note, not all small apps use web services. The 120 apps use about 4,600 unique services, and 98% of them are from the first 4 types listed here: web requests, queue interactions, databases, and web services. Intuitively, you may think that the services that are used by the most apps are the most important services. Here's a list of the top 15 web request services based on how many apps use each service. As we will soon see, these are not the top 15 most important web request services. Ultimately, we need to explore the links between all the services in the ecosystem, so we need to perform a link analysis. One of the earliest forms of link analysis involved citations, whereby the impact of an academic article was measured based on how frequently it was cited in other articles, with the goal of identifying the most important documents. Later, the hyperlinks inside web pages reminded Larry Page of citations. While he was developing Google's first search algorithm, he posited that not all links were created equal. For example, if the CNN homepage linked to a web page, then that page became more important than if just my personal blog page pointed to it. One of the easier graph computations to understand is Larry's PageRank, which has many uses beyond just ranking web pages. The page in PageRank comes from Larry's last name, not from the term web page. For example, which of these two entities is more important, Node 1 or Node 2? Node 1 has 4 edges pointing to it, and Node 2 has 5 edges pointing to it. So is Node 2 the obvious choice? What if I color the nodes like this so that you can see lineage easier? When I ran the PageRank algorithm on this graph, Node 1 had the highest value, so it is the most important. Even though PageRank was originally used for graphs with web pages as nodes and hyperlinks as edges, the math is entirely general and applies to any graph or network in any domain. So we can use PageRank to determine the importance of each service in an ecosystem of all the apps monitored by Dynatrace. Back when I was computing application complexity scores, I created a separate graph object for each application. However, to compute the service importance, I started combining together the networks used by each of the applications in the ecosystem until I eventually created one massive graph object with all 120 apps, 4,600 unique services, and nearly 15,000 links between them. When I zoom in, you can see the apps colored red and the services colored blue. By creating just one graph object, I can compute service importance relative to the entire ecosystem. Let's come back to our chart of web request services, which posits that the most important services are the ones that are called by the most apps. After computing a PageRank value for each service and then ranking the values within each service type, you can see that our intuition about importance based on a simple count is not always correct. Only 6 of the top 15 services that are called by the most apps are ranked in the top 15 based on the PageRank link analysis. The results are similar for other services, like web services and database services. Here's an example of the kind of insights that you can uncover by using PageRank rather than just simple counts. Let's look back at the list of 4,600 services. In the chart on the right, I'm displaying percentages of the 100 services with the highest PageRank values. You can see that 94% of the top 100 come from the usual suspects: database, web request, and web services. The most surprising difference is that even though database services only make up 17% of the total number of services, they account for 60% of the top 100 services. This video showed that there is a sound method for computing service importance, and it's also an example of the benefits of using a graph structure when the links between objects are just as valuable as the objects themselves.